Assalamualaikum and hi everyone. For our project, we chose the 8 puzzle problem, which is one of the classic example in artificial intelligence. So, the 8 puzzle consists of 3 by 3 grid containing 8 number tiles and 1 empty space. The main objective is to move the tiles step by step until they reach the correct arrangement. So, since only the tile next to the empty space can be moved, every action must be carefully planned. This puzzle may look simple, but in artificial intelligence, it is widely used to study how search algorithms work. It helps demonstrate how a system can explore possible moves, evaluate statistics, and eventually find the most efficient. So, for the problem description, the sliding puzzle has a long history, which is back to the 19th century. It was originally introduced as a physical puzzle game and became very popular because it challenges people's logical thinking and problem-solving skills. Over time, this simple game evolved beyond entertainment and became an important case study in computer science. In artificial intelligence, the 8 puzzle is often used to search techniques because each move creates a new state, and the system must determine which path leads to the final solution. This makes the puzzle a good representation of real-world problem solving, where multiple choices exist, but only a certain sequence of action will produce the desired result efficiently.
For my part, I will explain the implementation of search algorithms focusing on both, which is ununiform and informal search methods. For ununiform search, we have two, which is bird first search (BFS) and deep first search (DFS). For BFS, we explore node level by level. It uses a queue following the first in, first out principle. The advantage is the BFS is complete. It will always find a solution in one existing. It is also optimal, meaning it finds the shortest path. The drawback is that it requires high memory usage. And for DFS explores one part deeply before tracking. It uses a step and insertion. The advantage is low memory usage. However, it is not guaranteed to be optimal, and in some cases, it may be incomplete. Informal search, we have two, greedy best first search and also a search start. For greedy, the algorithm uses only the heuristic function, which is Hn. It expands the node that look closest to the goal. The advantage is fast editing, but the disadvantage is that it is not optimal and may choose the wrong paths. For A star combines the actual cost Gn with the heuristic Hn. For the formula, we have Hn equal Gn plus Hn. The advantage is the A star is complete and optimal, but the disadvantage is that it requires high memory usage. In summary, BFS and DFS are used when we don't have heuristic information, while greedy and A star are more powerful when we have heuristic are available. Which algorithm has a strong and weakness in between them, and the choice depends on the problem.
Okay, now we move to the heuristic design. We choose Manhattan distance as our calculation position for 8 puzzle. Okay, now we start with the definition. The sum of the absolute difference of the coordinates between the current position of a tile and its goal position. Okay, why we choose Manhattan distance as our calculation? Because first one is domain alignment. It perfectly matches 8 puzzle mechanic where tile move on the up, down, left, or right, and no diagonal movement. The second one is higher information density. More precious than the misplaced tiles. Heuristic because it measures the distance to the goal and not just a binary correct or incorrect status. Okay, as you can see, there's a mathematical formula for Manhattan distance. Okay, next. Okay, now let's take a look at how Manhattan distance actually work in our project. If you look at the first image, which is our initial state, you can see the most tile are already in place, except for two numbers, tile 5 and tile 8. They are already in a wrong position compared to our goal state shown on the right. To find the heuristic value, we refer to this calculation table. For tile number 5, it is currently at coordinate 2 and 8, 1, but its goal is 1 and 1. Using the formula, we calculate the vertical and horizontal distance, which give us 1 move. For tile 8, it is at 2 and 2, but it belongs at the goal 2, 1. Again, the calculation show it is only move 1 move away. For the other tiles, since they already match the goal state, their distance is 0. By assuming this up, we get a total vertical heuristic value of 2. This tells our A star algorithm that the goal is very close, allowing it to solve the puzzle efficiently in just 2 steps. And now we move to the heuristic properties. Okay, there's 2. The first one is admissibility, which is a heuristic is admissible if it never overestimate the actual cost to reach the goal. Since a tile must move at least 1 step for every unit of Manhattan distance, n is always the actual cost star n times n. And the impact is guaranteeing that the A star algorithm will find the optimal solution. Next, consistency. The estimate cost of reaching the goal from the nodes is no greater than the step cost to enable plus the estimate cost from the neighbor. And the impact is to ensure that once a state is expanded, the path found to it is the best possible and preventing redundant reprocessing of nodes.
Okay, next I'll present about part D, algorithm complexity analysis. As we can see from the performance comparison table, there are 4 algorithms, which is PFS, TFS, greedy best first search, and also A search star. Firstly, I want to start with PFS, which is expanded 9 nodes with a pass cost of 2. While it is optimal, it took 0.000280 seconds, which is slower than our informed search method. While DFS, this was the least efficient algorithm. It's expanded a massive 329 nodes into 0.00594 seconds. It had a pass cost of 320, which is far from optimal. While greedy best first search, this was very fast, expanding only 3 nodes. It used the least of memory at only 0.95 KB. While A search algorithm, this was our top performer, which is its match greedy search in expanding only 3 nodes, but it was the faster overall, clocking it at just 0.000163 seconds. Okay, next is key analysis point. Firstly is on efficiency. The high node count on execution time of PFS demonstrate the inefficiency of blind search for this puzzle. It spends resources exploring deep paths that were not optimal. Secondly is on memory. In terms of space complexity, PFS consumed the most memory at 124.88 KB. Meanwhile, greedy best first search was the most lightweight at only 0.95 KB. Lastly, on optimality, while BFS greedy and A star all found the optimal pass cost of 2, but DFS failed with a cost of 322. So it's proving that it's not an optimal search strategy for this problem. So in conclusion, our analysis confirmed that A search star is the most superior algorithm for the egg puzzle. So it provides the best balance between time and space complexity while creating an optimal solution. That's all from me. Thank you.